It is my great pleasure to introduce tonight's speaker, Dr. Gregory Retallack. Gregory Retallack is, I would say, a Renaissance man, but he probably goes back to the Proterozoic.
Again.
Greg has literally written the book on paleopedology, where pedology studies soils as a natural unit on the landscape. Think about that landscape being buried by sediments and then turning into rock and preserving the history of what the environment was like at the time the soil formed. Where in pedology and in many of my colleagues who are in quaternary geology, we're looking at things that are less than 2 million years old. Whereas Dr. Retallack looks at things that are 2 billion years old and possibly older. Greg is from Australia originally, born in Hobart, Tasmania, and then moved to the Sydney area. He has a Bachelor of Science in Biology
and Geology
from Macquarie University, and then a Bachelor's Honors Thesis, and then a PhD from the University of New England in Armidale. He came to the U.S. for a job in northern Illinois, didn't like it, and so toured the U.S. on a lecture tour for about a year before becoming a postdoctoral researcher at the University of Indiana.
Indiana University, yeah.
Indiana University. Mm-hmm. And after that, became a faculty member in the Department of Geology at University of Oregon. Go Ducks. He's been there since that time doing amazing things. I asked him this morning whether he slept at all, because based on his CV, it's amazing all the things that he's done. He's even had a fossil, or actually multiple fossils, named after him. So, Greg.
Thank you, Janice. It's great to be here and to meet with Janice again. Last time we was 1991 at a Sols meeting in Denver, and she walked out of my life and haven't seen her since. She hasn't changed a bit. Yeah, I used to go to some of the soil meetings, but I do paleopedology, as Janice just mentioned, which, of course, was the avocation of Humbert Humbert, who was the hero of that wonderful novel, Lolita. And the reason why Nabokov chose paleopedology as being his avocation is because it was the most obscure thing that he could think of that anybody could do. And I hope you'll agree with me after my lecture. Yes, it's pretty obscure, but it's really interesting, even more interesting than Lolita, because we can actually see the history of life on Earth back to the very beginning. And I mean that literally. I'm going to try and tell you that life evolved from soil, and we are, after all, just soils grown tall. A lot of this stuff is a little controversial. Don't mind that. That's why I like it. The problem that we've had in the past, I think, is that there has been a mindset against fossil soils. A lot of people have the view, for example, that the early Earth was as barren as the surface of Mars. We see these sorts of quotes quite often. The second quotation is another one that sort of says, well, there was nothing on land. It was pretty much a desert until early land plants in the Ordovician or Silurian. You've probably seen the documentary with Sir Richard Attenborough and others maintaining that it was a desert until the land plants came on board. Of course, we have a long record of life on Earth in other places, and that record is entirely aquatic. And the reason why people think it's aquatic is because they have a mindset of what we should look for early life on land. And it's this. It's these stromatolites, these famous microbial constructions. There are modern ones here at Shark Bay, and we have ancient ones going back 3.5 billion years. And if we're lucky, if some of these are silicified, we can actually see the microbes. These are filamentous bacteria. People have thought they might be cyanobacteria. I think they're more likely to be sulfur bacteria for reasons that I'll get into in a little bit. The thing about finding these things is you have an attitude of what you're looking for, you go, you find it, you find a stromatolite that's somewhat silicified, and bingo, you're in luck. You have an ancient record of life in the water. Sadly, this can only take us so far, and people have been doing this for a long time. Bill Shopf, one of my personal heroes, he's in all the textbooks, and I got this quotation from him, has been doing it since the 1960s with great success. And others are now looking for this kind of thing on Mars. They're not going to find it because, of course, Mars is a soil planet, not a water planet. But I think the problem is that we've been sort of fixated on this model right here. This is a microbial mat model. The microbes are aquatic, they're completely submerged. This model is all wet all the time, pretty much. Maybe at low tide they're a little bit exposed, but the mat is not fully integrated into the sediment itself. There can be crystals and things, there are roll-ups, it's undulating. You get these stromatolitic growths where there's gas production that domes this mat up like a carpet would bulge if there was some sort of gas coming out of the bottom of it, and they form these layered and stromatolitic layers within the rock. This is my model. I have another idea of what we should be looking for. We should be looking not for microbial mats, we should be looking for microbial earths. And here in Utah, you know about these things. They're in the canyon lands. They're in a lot of the desert landscapes of Utah. The BLM has a slogan, "Don't bust the crust." It's a microbial soil mixture that is not a mat. The microbes are interstitial. They are not forming a felted surface. They are actually in between the individual grains. The mats can include some quite sophisticated organisms, lichens, as well as these cyanobacteria and simple microbes. But the idea of a microbial mat is not to form a surface, but to form a profile. The whole profile is what you're looking for, a profile of differentiation from a land surface, so that if it weathers, it'll weather this way. It won't roll up, it won't come off in flakes. It's very different in its texture, and that's because it's non-marine. And it'll be associated with a whole soil profile, some 20 to 30 centimeters thick, maybe with calcareous nodules, otherwise known as caliche, in the subsurface, and there'll be a succession of these. A surface which is mixed up with rhizine traces and with microbes, and then a surface down in here which is sedimentary. So there's been a flood of some sort of aquatic deposition on a terrestrial environment that laid down a whole bunch of new material, and then the microbes took over and they altered it. We're interested not in the sedimentation process that produced the parent material, we're interested in what did the microbes do with the stuff that they actually got. One of my favorite pieces of fieldwork on this was actually when I took my two sons, 20-something sons, to Burning Man, which I got to claim as a tax deduction, which was pretty awesome. It turns out that your BLM has a large booth at Burning Man because the BLM has to approve the activity of Burning Man Festival on the playa and has to be completely cleaned up. But as a part of their public relationships at the Burning Man Festival, they offer excursions, which I thought were really very well done by quite knowledgeable people. And they took us out in this BLM bus. Look at that. That's something out of the 1950s there. And they showed us the microbial earth and then the microbial mat. Right here by a spring, there's a microbial mat, somewhat churned up by the action of livestock. And then this is a microbial earth. Look how different they are. These are green and felted mats that are submerged. And this is a microbial earth. It's got cracks that have healed. The whole thing is cracking and then healing. The microbes are growing into it. The microbes are growing out of it. The microbes are at some depth in the profile itself. It's quite a different search image if you're looking for something in the ancient rock. We're looking for these microbial earths as far back as we can go. This is one form of microbial earth which is very well developed, and I'll show you examples of this kind of microbial earth that go back some 2 billion years or so. The playa itself, where the man burns, and he's just down there a little way, is also a microbial earth as well, but it's a very simple one. It's only about 2 centimeters thick. It's dominated by microcoleus, which is a very rugged cyanobacterium that can stand desiccation and goes dormant until the rare occasion every 20 or 30 years when the playa is actually full of water and it forms this kind of crack-like thing. And also in here are brine shrimp and ostracods and other creatures that revive when the water comes in. Creatures are not afraid to go out of the water, and they weren't afraid to get out of the water very deep in geological time. These things have a long record, these microbial earths. Now, we can see these things in other countries too. This is Australia. I was born in Tasmania, which is down there. Sydney's here. Adelaide's here. If you take a transect from Sydney all the way out to Adelaide through here, you go at first in forests here, and then you get through a lovely vegetation type which is called the mallee, which is a very open woodland. And there's a whole variety of different sorts of microbial earths in the open patches between the trees of the mallee. Look at this lovely lichen here growing out. This is a microbial earth texture. There's a lichen here. There's more lichens, actually mosses in here, golden moss, Bryum aureum. There's a system of cracks. There's a kangaroo pellet right there. These are not preserved very often. A single kangaroo can destroy that. If I'd stepped on it, it would have been toast. If it had been grazed at all, this wouldn't be preserved. But in a natural state, lichens and other quite complicated creatures can grow out in these open soils. Lichens are not only growing on rocks. Here's another example up in this mallee forest here. And as you go further out to Mungo Lake, there's saltbush. It's called bluebush out in here, Myria, different genus than what you have here in Utah. And this is what the surface looks like. It's pustulous, with a whole variety of lichens and cyanobacteria that are forming a desert crust kind of ecosystem. Now, where I really started to get controversial was when I started to write about these sorts of things in relation to these wonderful fossils that are in all the textbooks, commonly called Ediacaran fossils, but that's kind of a misnomer now because we have an Ediacaran period. So any fossil found in the Ediacaran is an Ediacaran fossil. And there's tubes, and there's coral-like things, and there's a whole bunch of stromatolites. There's a whole bunch of Ediacaran fossils. These I like to call vendobionts, which is what Adolf Seilacher called them. And these are the mysterious ones, the quilted ones, that have high relief. They're preserved in the sandstone beds above what I regard as paleosols. And I'm thinking these are probably not aquatic creatures, but perhaps terrestrial. Here's the typical textbook view of what they were like. So when people see these kinds of things, this is what they look like in the field. This would be the sole of a bed of sandstone that has some of these Ediacaran fossils. Since they spent their youth as blonde-headed, stumpy-wumpy, real-gone surfer boys, in the words of a popular song, and like to cruise the tide pools and were familiar with invertebrate biology, they see sea pens and worms and mollusks and starfish and other worms here, and these funny things here, maybe some sort of anemone. So that's one interpretation. That's the one that's in all the textbooks. However, there are other interpretations. Distinct creature that is at the stem of the Metazoan clade. That's a very popular view. I think not, however. And I think not because I visited the places where they're found, and I saw not a whole bunch of marine beds with microbial mats and with typical marine textures. I saw a whole bunch of paleosols. How do you recognize a paleosol? Well, there's a bunch of them here. This is where the fossils are. Those are the horizons, and this horizon goes all the way through here. This one goes all the way through here. There's fossils all along there. There's several up in there. How do you tell a paleosol? Well, three things. Root traces, well, that's not too good in the Ediacaran. There's no plants. We're back 550 million years here. But there are filament traces, and there is disruption of the surface. So the surface is a little bit massive. Soil structure, this is the part that geologists were never trained in. Soil structure is a thing. It really is a thing, like PEDs and cutans, like clay skins and clods. I once tried to persuade people that we should use clod skins instead of clay skins, but I don't know, it didn't go anywhere. Cutans are good, I think, but they are a real thing. And it's that soil structure that makes the beds look kind of massive. So this is bedded. That's the regime of sedimentation. Here's massive. That's the regime of soil. Here's bedded. Here's massive. This is actually a set of convolute laminations, which I believe is a periglacial paleosol. And then here it's massive. And then the bedding picks up down here. You can see the individual layers. It's bedded down through to here and massive down in here. And then there are, and other soil structures are nodules, like caliche nodules. We have those in these beds. We also have crystal casts, like sand crystals, like the Oklahoma desert roses in these paleosols. Those are other soil structures. And then there's profile form. A paleosol should have a sharp top to it and a gradational change down into sedimentary parent. A sharp top, gradational change. The others are a little bit more subtle in this particular view, but I have other views. The one thing that people really like about these paleosols is the sand crystal thing. In marine rocks, where we get a precipitation of something like a gypsum crystal, which is what these were, the gypsum is able to force the sediment aside, and the gypsum comes out clean and pure and virginal and limpid. You can see through it. It's lovely. In a soil, however, when a gypsum grows, it does not have the strength because the soil is dry. It will incorporate the sand grains that are already there in the soil, and that's what we call a sand crystal. Here's a bunch. Here's one here, one here, one here, one here. There's the top of the paleosol. It's red, and you go down to a horizon which is full of these things. This in soil science would be called a gypsic horizon or a BY horizon. Here are some thin section scans. These radiating things here are gypsum crystals, selenite form, which have a lot of included grains in them from the original soil. Here's another one. This is a gypsum here, which has a lot of included grains within it. These sand crystals, I think, are pretty diagnostic of paleosols. And I've had to really try hard to persuade my colleagues that these are soils and not just sediments. They're sediments too, but they're certainly not marine sediments. These are non-marine sediments that have soils developed in the intervals between flooding. I did all this kind of thing. Here's a nice diagram. Oh, these are the soil profiles. I give them names because I think they're like people, you know? And I give them Aboriginal names because, after all, these are the first peoples. They go back 550 million years, and each one is different. I try to document what the clay, sand, and silt proportions are, so you can see all the profiles are clayey in the surface, silty, and there's a lot of silt in here. And that silt is angular and, I believe, aeolian. It's basically loose. The degree of chemical differentiation of them is rather modest, but it's nevertheless pretty significant. The boxes here, I found the paleosols in cores as well. Some people have thought, oh, you could get this differentiation in the outcrop through modern weathering. That's a possibility, right? But there are cores that go down 300 and 400 meters through these rocks that are stored in the core shed at the Geological Survey of South Australia, where you can see the same features, and you can analyze that rock too, and it falls right on the equivalent kind of paleosol that is found in the surface. Each paleosol has a distinctive profile form, like the Moru. The Moru for here is quite sandy. This one has the convolutions, the periglacial convolutions. This one is quite clay. The Moru has gypsum. This one has calcite. Here's an Inga, which also has these gypsum rosettes. With this kind of data, we can actually start to figure out what kind of a soil it was and compare it with modern soils, and I won't bother you with soil taxonomy. But there are other ways of looking at these too, and I've had to try pretty hard because a lot of people who are used to the idea that these are marine fossils are not very comfortable with this idea. One of the really sneaky ways we can study a soil, and I won't belabor this because it's a little technical, is we can do a tau analysis. We can take a stable constituent and we can work out, taking that stable constituent, and that stable constituent was titanium in this particular case, how did everything else change? Since we have a density, we can work out epsilon, which is the strain, and there's three ways you can strain something. You can expand it, or two ways you can strain it. You can expand it or you can contract it. So if the strain is down here, that means it collapsed. If the strain is up here, that means it expanded. And then for each material, like magnesium, calcium, sodium, and potassium, we can work out whether that material was lost from the profile with respect to the origin, which is right here, or whether it was gained. Since just about everything falls in this quadrant, that is the quadrant of soils. And these are the different paleosols. I've got some Miocene paleosols for comparison. The open signals are the symbols are the Ediacaran paleosols. They're all in that bottom left-hand corner. Sediments, on the other hand, would be up here. And I do have some sediments just to show you that that worked as well. But mostly I was dealing with paleosols that are mimicking pretty nicely the kind of soil development that you get in the Miocene. Soil development is going to deplete materials as they weather away to feed the ecosystem, and the whole profile is going to collapse because it's going to be removing material. It's not going to expand as it would if it were a sedimentary bed. Here's another really sneaky way to see a paleosol, and I think this is really super, and we want to do more with this. We have caliche nodules in the paleosols. I've got Ediacaran ones, I've got Cambrian ones in here, Ordovician and Silurian as well. It's very interesting. If you look at modern soils, there's a super tight relationship between the oxygen isotopic composition and the carbon isotopic composition, both with PDB. I've been puzzling about this for quite some time, and that's why I think these are paleosols, because they have this super tight, look at those R-squareds, 0.9, 0.8. They're super tight in soils. They're really sloppy if you take a marine carbonate and you weather it. You get the same thing, because the cyanobacteria within the carbonate will tend to sort of impose that, but not quite so well. It's also kind of sloppy if you alter limestone with meteoric water. The relationships are not nearly so tight. This is what a marine carbonate would look like in the modern with open signals, and in the Cambrian, we know that's marine because there are marine fossils in it, and in the Ediacaran, you're kind of begging the question as what's marine and what's non-marine. That's the issue, isn't it? It forms a scattershot in a marine environment. And then here's a methane seep right here. In a methane seep, the oxygen is constant and the carbon varies considerably. This is a fully aquatic system. We find this also in siderite in soils. These are pretty clearly soils. The reason for this relationship is because the enzyme rubisca, which is found in all sorts of organisms, even cyanobacteria, it selects for isotopically light isotopologues of carbon dioxide. So it doesn't know if a carbon dioxide molecule that's coming its way is light for carbon or oxygen. It just wants the light one, and it fractionates against the light one really quite well. At the same time, that's how you get this really tight relationship. All plants do this. Even cellulose has this pattern, as John Ehlinger at the University of Utah has shown really quite elegantly. This is, I think, really strong evidence that the carbonate nodules in the Ediacaran paleosols were actually paleosols. They're not like marine at all. They're not even like altered marine. They're like these modern soils. There are other things too. Here are some Ediacaran fossils. Here's one here, one of these discoids. Here's a Rugoconides here. Typically, when you get these fossils, they're on a odd-looking surface, which is called old elephant skin. That means it's cracked, it's dimpled, it's got pressure centers, it's got expansion centers, it's rumpled. It looks like the Burning Man microbial soil surface that I showed you, and like others that I've shown you from Australia. I like to call this I like to use a trace fossil name. It's actually been named in the literature. It's this one here. And I think it's diagnostic of soils. You don't get this in marine environments anywhere. In marine environments, you get wrinkly surfaces, and you get bioturbated surfaces, and you get granular surfaces, but you don't get this particular kind of old elephant skin texture. And my colleagues who have been really upset at everything I've done have gone after me with several really sophisticated analyses that open up new ways to see paleosols in the record. Remember I said there's no root traces in an Ediacaran fossil soil, and that's a problem because we use root traces a lot if we're looking at a paleosol in, say, the Cretaceous or the Jurassic. This was Lydia Tarhan's work, which is quite brilliant, actually. So she looked at holdfasts. This is an Ediacaran holdfast of one of those frond-like fossils, and it's been covered by this bed here. And she analyzed the germanium to silicon ratio on this transect. Now, in the grain itself, which is a grain that came from granite of the craton, it's very low. It's less than 1, and that's actually pretty typical. In fact, the values of less than 1 are found in aquatic environments all over the place. They're found in many igneous rocks. This value here, up to 10, in this early diagenetic cement, is only found in soil. Here's what it looks like in even lakes. You get low values. In streams, in the ocean, in diatoms, in radiolaria, always the germanium to silicon ratio is less than 1. It's only in soils that you start to get the big numbers, up to 50 in some cases, because of these orthogenic phases and because the germanium is not swamped by the silicon like it is in aquatic systems. This seems to me to be a very promising method of going forth, and it's been demonstrated for these Ediacaran fossils here. And I've got a whole bunch of polished thin sections ready to roll as soon as I can rub together the $1,800 a day I need to run the machine to get these analyses. So there are we're also looking at magnesium isotopes. That's a whole new project too, to see how we can recognize these soils that are weakly developed. At this particular location, there are no nodules, there are no sand crystals. The soils are thin, and they are what we would call endosols in the modern environment. They haven't formed over a very long period of time, but they do have the germanium to silicon isotopic signature of the signature of a soil. So here's my reconstruction. It's a little different from those waving fronds colorful fronds in a shallow sea. Here are my paleosols reconstructed as they would have been. In an environment which would have been a floodplain, a whole variety of different sorts of soils, some with gypsum crystals. These are the immature ones that we can now apply germanium to silicon to. These are the ones with calcic nodules, gypsum nodules, and then the periglacial one. And sitting on top of them are these Ediacaran fossils, which I think were some sort of a terrestrial organism, which rules out a lot of the metazoan idea and invites the idea that they may be comparable with lichens, particularly these crustose lichens. Well, there are other places where you get these Ediacaran fossils. In Newfoundland, for example, we get these lovely fractal things. This is a set of beds that has been interpreted as a sequence of paleosols. So that's a bit difficult for my idea that they might be fungi or lichens, right? And these are very fine-grained. So the idea is that these must have been a long way from shore. They must have been way out in depths of maybe 6 or 7 kilometers of water beneath the photic zone. They could not be fungi. They could not even be photosynthetic. The only other place where you get sediments that fine-grained, of course, are tidal flats, which are exposed between the tides. And I went there to try and figure out which of these possibilities was likely. I had reason to go there, actually. It's a big, thick sequence of Ediacaran rocks in Newfoundland, and it's quite well dated. There are several levels that are red. That's a bit curious. They're red in a way that is like soil. If you use this index of highly mobile versus total iron, they fall in the modern soil field. If you use this index of C to S ratio, which has also been done, they turn out to be, in some cases, freshwater and in some cases intertidal. And interestingly, the indications of shallow or non-marine environments are where the fossils are the most diverse. There's also some indications down here where we don't have any fossils. But I took a rather more pragmatic approach to the problem because for my 37 years in Oregon, I've been in a department of volcanologists and volcanic processes. And these are volcanic rocks, and these would have clues, I think, that would be very helpful for discerning whether they were marine or non-marine or intertidal. And here's one clue. This is a thick tuff. The Ediacaran fossils are right on this plane here. There's a lot of pyrite down in here in bands, and this is a tuff bed which I took and slabbed and polished, and you'll notice this interesting thing here. That's a gas escape structure. This could not possibly form in a tuff, a volcanic airfall deposit that fell through any amount of water, even a meter. All that gas would be out. Furthermore, if you look carefully, it's a bit grey here and it's a little lighter here, but there are big grains and little grains throughout. See, there's a big grain, big grain, big grain, and the little grains are all around them. That's not possible either. If this had fallen into water, the big grains would go to the bottom and the little grains would be at the top. It would be graded. It's ungraded, and it has these structures that are like gas escape structures. Here's more. This is what it looks like if an ash falls into water. The fine materials here, a bit of pumice might be up in here, but then it'll grade itself according to grain size if it falls into water. This is an Oligocene example quite close to Eugene, Oregon. Here's another graded bed here. This is a beautiful graded bed there, fine through to coarse. But in the Ediacaran of Newfoundland, we find this. This is a tuff which has volcanic lapilli. These are the lapilli, these big round things. They're not pumices. They're actually not vesicular, like these vesicular pumices here. They are silty volcanic stones. And these are known to disperse rapidly if they fall into water, and yet here they are intact. Furthermore, if these had landed in the water, they all would have gone to the bottom. You'd have a graded bed of these things. And we don't. They're scattered around like plums in a pudding. Here's more. These white flecks beneath this surface here, there's some soft sediment deformation there. I think this is a paleosol for the reason that these are sanidine grains. Sanidine is a high temperature, high pressure form of feldspar, and they're scattered around. They did not go to the bottom. Here's the sanidine in a thin section scan. There's a fossil stalk there. Here's a sanidine grain here. Here's a sanidine grain there. Here's a sanidine grain there. They're scattered around. They're not going to the bottom of the bed. This is like tuffs that we have in the John Day Basin of Central Oregon, where the material is completely non-marine. Here's a volcanic bomb. This is actually a spindle bomb. We have to be within about 7 kilometers of the edifice, and that thing has to have traveled through the air to shape up like that and then plump into the tidal flat sediments. Here's a big scoria bomb from a block and ash flow that's 10 meters thick in these same sediments that have the Ediacaran fossils in Newfoundland. We're close to subaerial volcanics. This is not submarine volcanism. We know what submarine volcanism looks like. A lot of breccia, a lot of phreatomagmatic alteration, a lot of zeolites, a whole different profile. This is all subaerial volcanics. So Newfoundland back in the Ediacaran was like my hometown, Eugene, Oregon, home of the ducks. It had a subduction zone. It had a volcanic arc, which was fairly close, and the Ediacaran sedimentation was in a 4-arc basin like this one here. This is the Coast Range here, and the Olympics up in here. The Coast Range in the Ediacaran time was not quite so strong. It's represented by an arc of granites that were uplifted as a fault-lifted block in a subduction zone of Ediacaran age. Now, I had a permit to go there, and I actually collected the beds. This is a field bed here. And here's a bed right here. This is the bed that has the Ediacaran fossils on it. There's several. It's green, and then it grades down into red. And then you get down to this sand, which has quite a sharp top there, and then it's got all this turbulence. Here's another sharp sand, sharp on the bottom, sharp on the top. It's not like a turbidite at all. If it were a turbidite, if it were a deposit of a turbidity current in a deep ocean, everything would have settled out graded, as it does always in water. It's got a sharp top. These particular beds here remind me of this. These are tsunami beds. We're dealing with a subduction zone. We have tsunami beds, and we have thin soils that, like here in the Ediacaran, that look quite a bit like these soils that we get in modern Thailand. These are soils that would have developed between earthquakes on a subduction zone fault environment. I also polished these slabs, which was kind of fun. I have a whole selection of polished slabs, and I donated them all to the museum in St. John's in Newfoundland. Here's the paleosol, sharp top, gradational change downwards into bedding, and then here's the tsunami bed, sharp on the top, sharp on the bottom. Another tsunami bed, sharp on the bottom, sharp on the top. Here's another sharp top to the paleosol. Look at all this lovely mottling. These filament traces down through here. The glaciation, the green color here, from organic matter down into this. And it's not a graded bed in terms of grain size. It's graded in the fact that you don't have bedding here, and you do have it here. And the contact between the two ungraded or unbedded and bedded is kind of insensible. These are the sorts of soils that you would get in a coastal or tidal flat kind of environment. Here's some more. Sharp top, grading down into laminated, sharp top. Look at these lovely mottles here. That's a soil feature. And then you get down into the bedded material here. These are paleosols too. like the ones in Ediacara. They're paleosols, but there are different kinds of paleosols because they're non-calcareous and they're non-gypsic. And they're not that well developed. I envisage Ediacaran of Newfoundland looking quite a bit like this. Here's the Harbour Main volcanic arc, which would have been like a shutter ridge, like the Coast Range of Oregon. And we're dealing with some that are pyritic and weakly developed, that have a lot of pyrite in the subsurface. That's a pretty classic tidal flat soil. And we're dealing with others that are mottled to fully red as you go further inland on a coastal plain, which was episodically interrupted by tsunamis. So far, so good. I've been to Namibia as well and found paleosols there. I'm working my way around the Ediacaran of the world, but I think this idea has legs. So far, nobody's been able to falsify it, and I've been able to continue working on this really interesting problem. But I must say, it's still pretty controversial. 3 papers this year have tried to interpret the Ediacaran fossils as a variety of different organisms, and everyone is different. They can't agree on how they grew or what kind of organism they were. I think, for starters, they were terrestrial, and that's what's been throwing a lot of people off the trail of the real answer. Now, I want to step way back now, back to 2.3 billion years ago, which was a time of pretty seminal change on Earth. We have a big step in the amount of atmospheric oxygen that was probably due to the evolution of cyanobacteria, including those stromatolites, which I talked about. We have a record of those going way back for a long way. And a lot of people now are pretty confident with the rather Gaian explanation that cyanobacteria transformed the planet, that the evolution of cyanobacteria created oxygen for the first time and poisoned out the opposition, which would have been a sulfur bacterial world before then. But what about the land? Did the land have any role in this? I think it probably did. And I think it did because of this rather wonderful paleosol that I was introduced to by Andy Button in 1984. Here's the paleosol here. What's lovely about this one, it's in a road cut in a highway in South Africa. There's the top of the profile. And look how interesting that surface horizon is. It's black, then there's a dike, then it's black. This was a crack that's filled with sand from above. And then we know what this is. Even Janice knows what this is. It's a vertisol. It's a paleosol. These are the swelling clay soils that are common in Texas and other. I think we visited some in a soil pit near New Braunfels, Texas, on one of those micromorphology trips. And here it is, 2.2 billion years old. It's a bit beat up. It's been metamorphosed, and you'll see it gets worse. It's recrystallized pretty significantly because there was this great big intrusion here called the Bushveld complex that came in and heated it up, and it was buried by about 10 kilometers of sediment. So that makes things a little bit dicey, but this physical structure is really quite tremendous. I mean, that is clearly a paleosol, and it's been a very important paleosol. Dick Holland, a former colleague I worked with a little bit from Harvard, used it as a linchpin to try and get this kind of idea of the oxidation of the Earth from paleosols. These are all paleosols, and some of them are oxidized and some of them are reduced. And from that you can calculate the redox threshold composition, which changed through time. I put the waterfall onto paleosol down on this side. He puts it up there, but it doesn't matter. We've got others to constrain the curve. Something is happening around about 2.3 where the amount of oxygen seems to rise and the amount of reductance naturally in the parent material cell can't overcome that obstacle. So we can calculate oxygenation from this method. People have done this many times now, and it doesn't appear to be quite as profound as Dick Holland formerly thought. It appears that we only went up to some 4 or 5% oxygen. Now we're at 21%, of course. But it was a big deal because it changed everything. It changed the whole biota of the land surface. And here's my reconstruction of 2 kinds of soils that would have been on that ancient 2.2 billion year land surface. Here it is in the field. This is the Miocene paleosol here, and but it's nice and fresh here because it was a big major highway cut when I examined it in this little rental car from Joburg. And it occurs right here. This is a thin section scan, and you have these clasts and you have this bedding in that surface swale of the vertisol, and then you have these funny things here, these ovals, which I've called dyscagma. Those really took my fancy. We know quite a bit about this soil. We have tricks now to get a lot of information from soils. We can calculate from chemical composition that it was a humid soil, that's the mean annual precipitation, that it was a temperate soil, that's the mean annual temperature. We can work out the oxygen composition and the carbon dioxide composition of the atmosphere by using rather complicated algorithms, which I won't go into. And it's quite a beautifully developed soil with quite strong mineral and chemical zonation. But the part that I was really fascinated with are these discoids. Could they be endolithic organisms, modern organisms that crept into the rock? That's a possibility. We have endolithic lichens in Antarctica. We have them actually all over the world. I don't think so. And the reason is, you can see in thin section, here's a dike of chloritoid, which is 2 billion years old at least, associated with the Bushveld complex, and it cuts this discoid, this kind of discagma fossil here. So this came later than this. It has to be at least more than 2 billion years old, so it was in the Paleosol. And then if you look at backscatter, this, what looks dark and like a solid wall, is actually made up of all of these high Z heavy grains. It's all recrystallized. It's been recrystallized metamorphically so that we lose a lot of structure. We did chemistry on them, and it turns out that the walls are rich in titanium and iron and manganese, and that's a mineral that sometimes people call bernacite. The matrix is largely a potash-rich material, which I think was probably originally illite. So we've got a bit of an idea about what it was like as a soil. So was this an organism? Well, there's several different ways of telling whether you have an organism in the past. What you expect to find if it was an organism and not just a crystal or some sort of mineral growth is you expect to see some form of taphonomy or alteration. You expect to see well-preserved ones and poorly preserved ones because all organisms can be degraded by other organisms. And I think we see that pretty well developed through here, and then fading, 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 fading. You can see that they're decaying in the soil itself, in different parts of the soil. The size distributions, normal distributions, a little bit skewed to the right. This matches actually pretty nicely comparable lichen-like fossils, for example. These are the fossils here. Here's the modern here. The size distribution looks pretty good. It's not a very broad distribution. It's a narrow range. That's pretty typical for biological entities as opposed to minerals. We were really hopeful to find sex, but sadly, it's like those videos that are posted online where the genitals are all blurred out. They're blurred out by the recrystallization. And so here it is. Here's the sex. Sex is going on here. I'm really confident because it's in the right place. These filaments that go up through here, these should show apothecia if they were fungal. They should show different zygospores. They should show something, but what you see is kind of a mess. It's just blurred out, so the Discagma sex is sadly still elusive. Maybe it'll be discovered in some place where they're not so strongly metamorphosed. Now, for many years I didn't publish this because they're black on black, and it's very hard to illustrate them, let alone see them. So here's one here in a slab. Here's another one. Here's another one. Here's another one. Hard to see, right? That wouldn't convince anyone. And sure enough, the reviewers hated it. Here's a bunch of them. They're connected in stolons. And I'll pardon you if you can't see that well. It's really difficult to see. So I had to actually go to the cyclotron at Berkeley and image them with a technique which is pretty similar to that of a CAT scan, where you have a cyclotron high-energy rays that go through the specimen, and then you can form this three-dimensional image. And that's pretty fascinating, I thought. Kind of surprising after looking at these. Look at this kind of inflection there. I didn't notice that when I was looking at the actual specimens. There's actually probably a filament that goes off there. There's another one there. These are the different views you can see here. This is the serial sections right here. Here are some more of these filaments that are going out the base. Here's the recrystallization, and there's a detail of a highly recrystallized one. I think they're organisms, and I think they were a system of urn-shaped hollow structures with apical filaments and with attached filaments on the side. This is a complicated organism. This has to be at least a eukaryote. This is the oldest known eukaryote, 2.2 billion years. In the marine environment, the closest candidate is 1,600 million years, 1.6 billion. This is 2.2, and it's on land. It's in a paleosol. I think it made a big difference. They're compacted in a very strange way. This is what happens to a log. If you compact it 4 kilometers, 8 kilometers, 12 kilometers, 16, it flattens to about 1/10 of its diameter. If you take a lichen fossil, and here are a bunch of them we know about, it doesn't flatten nearly so much because lichens are made of chitin, like your fingernail, like a rhino horn, like a trilobite. It's tough. Here's Dysgagma buttoni on that track. It's flattening like a fungus, not like a log, and certainly not like a jellyfish. Jellyfish jellyfish should be right up against this axis. In fact, there's 2 jellyfish there in the Pennsylvanian that were in a siderite nodule which cemented them a little bit. Jellyfish cannot, any kind of metazoan creature that's soft-bodied and doesn't have a skeleton, cannot withstand being buried to 10 kilometers or so and still maintain any thickness at all. So what are they? Well, kind of a mystery. Here are some fossils that it's similar to, so there's not just one of them. Fungal affinities seem pretty good to me. Slime molds is a possibility. Here's some slime models growing on a Douglas fir stump here. Here's a lichen which has got the hollow structure to it. This is Cladonia, and it's got this kind of cup-shaped thing. I kind of like that. However, I don't think it's an ascomycete. This one I really like, though. This is a thing called geosiphon, a very little-known glomeromycotin fungus, which is related to mycorrhizae, for example. It has a big hole in the middle in which it has captured Nostocalin cyanobacteria. It's a lichen-like creature in that it is a symbiosis between a fungus, which is related to mycorrhizae, and cyanobacterium. I think that's quite possible for this. Fungi, of course, are eukaryotes, and they are quite commonly symbiotic with, and they're not photosynthetic themselves, but they're quite commonly symbiotic with photosynthetic organisms to give that appearance of being rather plant-like, green, and photosynthetic. It's really the cyanobacteria or the algal partner that does the photosynthesis. So here it is, my reconstruction of Dysgagma buttoni with these rather vague filaments that go in the top itself. Now we have the first eukaryote. It's probably a photosynthetic organism. I think this is going, and if these covered the Earth in any abundance, this could really go a long way to explain the great oxidation event itself, because you have so much more photosynthetic capacity on land than you have in a few shallow bays where you have the stromatolite or two. So let's go further back. Further back we have more paleosols. This is a very famous one at 2.8 billion years. It's called the carbon leader. It's this very carbon-rich seam right here beneath a fluvial sandstone. The paleosol is this green stuff which is immediately below it. There's been some doubt about whether these were actually organisms in place. They look like organisms. Some people have argued that they were blebs of hydrocarbon that were transported like oil and landed in this particular place. I think that's pretty unlikely. Here's a polished slab in which a metamorphic vein cuts across it. They're growing on the top of this paleosol, basically, and they're covered up by fluvial deposits. We don't know quite what they were. This is a reconstruction that Horbauer did. I think they might be some sort of columnar biofilm. We do know that they're organic. We have this lovely carbon isotope composition. We have pristane and phytane, which are both chlorophyll precursors. Maybe actinobacteria. I'm still working on them. I managed to get a specimen when I was in Johannesburg last year, and we plan to do a lot more with it. Further back still, 3 billion years. What are paleosols like at 3 billion years? Well, they're pretty odd. This is a study I did up here in Western Australia, and I've got quite a few more of these. They're in this kind of a landscape, in that position there. Sharp top, gradational bottom, sharp top, gradational bottom, and these are all crystals in here. Crystal outlines. They're hard to see. I'll show you some thin sections in a bit. Here are the crystals. A radiating rosette of crystals. They're all turned into chert now. It's beat up. It's very old. The crystals have been dissolved and then replaced by chert. There's crystals there. Here's one that has kind of a gypsum-like form to it. These, we know from their hexagonal outline and their elongated outline, those are narcolite, which is a sodium carbonate mineral. If these seem familiar to you, well, think Great Salt Lake. These are soils like the soils around Great Salt Lake in Utah. lots of sulfate minerals in these Archean paleosols. And we have a lot of these now, a lot of these soils in which there was acid sulfate weathering going on, not hydrolysis, not benign soil formation with carbonates, but sulfate weathering seems to be very widespread as you go further back in time. This one was exceptional because it had fossils in it too, this paleosol. And the fossils have been known for quite some time. There are these round ones, big round ones, small round ones. These are quite lovely. These elongate spindles, I like to call them, sometimes arranged along threads. And then there's all of these framboids in there as well. Chris House of UCLA did a wonderful study of these fossils. We are now able to get a carbon isotope composition of an individual cell, which is pretty extraordinary. We focus the laser on it and run through the mass spec, and so these turn out to be super light, minus 44. They have to be methanogens. These turn out to be about minus 34 or so. They have to be sulfur bacteria. These are all over the shop. I think these were actinobacteria, like these modern ones. They're all over the shop because you are what you eat. If they're eating methanogens, they're going to be super light. If you're eating sulfur bacteria, you're going to be super heavy. It's going to be a complete ecosystem we have here because we have the producers, the sulfur bacteria, and we have the consumers, the actinobacteria. It's a complete ecosystem on land 3 billion years ago. I did a whole bunch of chemistry on it and then cell counts as well. I'll gloss over that in the interest of time. But this is what I think the world was like 3 billion years ago. Here are some of the key fossils that we have, some of the different kinds of soils from very weakly developed through crystal-rich gypsids, through these narcolite-rich, I suppose we'd call those gypsids as well. Salt terminology is a little vague on that. They're all drab, no oxygen in the atmosphere to speak of. They indicate high carbon dioxide levels in the atmosphere, and they indicate a peculiar pathway of weathering which is known as acid-sulfate weathering. Quite common in playa lakes, in desert lakes, and in arid areas today, but widespread in the Archean on Earth and also on Mars. This is a map of Mars. You may remember the old Viking missions in the 1970s here in Utopia and Chryse. And then the activity now with Curiosity is here in a place called Yellowknife Bay. And when these images came beaming back from Curiosity and the data was made public in a series of papers in Science magazine, I thought, oh my goodness, we have a paleosol. Several paleosols, actually. Here's the sharp top to the paleosol. This is a sedimentary deposit which covers it up. There's another sedimentary deposit here. And look, it's infested with these sulfates. We know from spectral and also chemical data that that's basanite, which is a hydrated sulfate, not too different from gypsum. And they're growing in place, and they're obscuring the structure. There are dikes filled with gypsum that go subhorizontal near the surface and then vertical and wiggle around down into the profile like the cracks in a desert soil. Here's a tegmatically folded example of a gypsum-filled crack. That would have been a crack in the original soil. These are 3.7 billion years old from crater counts, and they look a lot like the soils that we have that are very highly silicified in the Archean of Australia from 3 to 3.5 billion years ago. The chemistry of, that was returned by Curiosity is really quite wonderful, and I did a tau analysis of this. Look at the error bars here from Curiosity compared with the Viking mission. They show very similar trends, but we have so much more accurate chemical analyses of these paleosols. Here is the tau analysis. Remember the trick here? If it's a paleosol, it should be in this quadrant, and they all are. If it's a sediment, it should be in this quadrant, and none of them are. You can also do it with depth. It's a modest amount of weathering, and we all agree, although we have different interpretations, that we're forming smectite, a clay, from the weathering of olivine, a very labile mineral. That's the soil formation. That's the extent of the soil formation. Pretty modest by modern standards, but nevertheless, I think, significant. If we go further back, there are other paleosols. They're not known as paleosols widely, but I think they are. They're called carbonaceous chondrites. 4.6 billion year old meteorites have this really interesting situation where you have these barred minerals of pyroxene and olivine. These are both pyroxene, I believe, and this is a barred chondrule, which is a high temperature phase with a weathering rind around it, and then a low temperature smectite and carbonaceous matrix to them. The high temperature minerals are the parent material, and I believe the creation of the smectite and the organic matter is created by an early form of soil formation on a planetesimal. They're all dated at around about 4.6 billion years old. That's the age of the chondrules. And then we have calcite dikes that run through them that have been dated by xenology as only 180 million years after that. So they're all really, really old. And we know the sort of environment where they form because the recent Dawn mission to Ceres returned lovely images of a planetesimal covered in this organic clay material. There's areas of gypsum that are exposed here and ice here, but this is just the sort of soil that we find on several asteroids that is one of the primeval paleosols of the galaxy. So, from here, what about the origin of life in soil? Well, I can't really give you the idea that it's well established, but I'm going to give you a fairy tale instead. And I'm indebted for this fairy tale to Graham Cairn Smith, who invented this idea. And it's the sorry story of lumpy, sticky, sloppy, and tough. So just imagine, these guys are out there, and gals, I suppose, why not? Are out there on the surface of a planetesimal at the very beginnings of the solar system. The planetesimal is degassing water into the air and also carbon dioxide. It's creating a dilute acidic solution, and it's starting to weather the primary minerals. The strategy of tough is this one here. That would be like a kaolite clay. And a tough one is going to actually mantle the grain like a quartz grain or a feldspar. And that's not a very productive strategy for making a soil because that'll choke off the supply of making more material. It can only grow by accretion. Sloppy is like a smectite that is super easily dissolved in water, and it just washes down into the profile. Now, the clays that are really interesting are lumpy and sticky. So these are smectite clays that are going to form near the surface, and when they are wet, they will expand to bridge the gap between the grains, and when they are dry, they will crack. They'll crack away from the grain. Pretty soon, you've got a kind of an evolutionary race here between lumpy and sticky, depending on the precipitation and all the other variables. You have an evolutionary process. These clays are evolving like organisms, and the stakes are high. There is very stringent natural selection in this system, and that's the missing element in every other theory for the origin of life. There's no natural selection. It has to happen just by chance. In this system, what happens is the patches of ground that have the most clay are going to persist, and the patches of surface that have the least clay are going to be washed away by the wind or by water or by flooding. Pretty soon in a system like that, you're going to have a planetesimal covered in carbonaceous chondrite, covered in clay, and then you can add organic matter to that because the organic matter can form by Urey-Miller syntheses, and the organic matter will have the same effect. It's sticky, like molasses on a cornfield. This is going to make a kind of a soil which is clay and organic rich. There's still a lot of water in here, even at field capacity. There's still water here to do very interesting biochemistry of all different sorts, and it's very strongly naturally selected to make a very complicated matrix which is evolving like life, and I believe could have created the very complicated materials like DNA and RNA and proteins that could do the same job. In effect, tropical rainforest is doing the job now that these clays did from the very beginning, augmented by organic matter by a process of natural selection like this. So I think the idea that soils were actually the source of life, that soils were kind of a proto-life, it's a theoretical one, but it's really worth considering, I think, as a way to get through the tangle of the origin of life. The big difficulty, as Jacques Monod said, is how to distinguish between chance and necessity. Life didn't evolve by chance. You have to make it a necessity, and for that you need natural selection from before the beginning, and this is a possibility for that. So this is my last slide, you'll be glad to hear, and whenever somebody puts up a slide with a lot of text, my heart sinks and I think, oh God, he's going to read it. Well, I'm not going to read it, I'm going to sing it. Where should I begin to tell the story of the life that was on land before the Cambrian explosion could expand? Was it as barren as the textbooks all demand? Perhaps not so. It was alive with large and tiny beings, with moisture, clay, and slime conditionings. Back to the start, life's favored places are in sun, rain, and mineral faces. Could it be that after all we are but soil grown tall? Thanks for your attention. That normally stops questions pretty well, but I'm happy to entertain anything you might want to ask. I managed to keep within the hour. I'm proud of that. Thank you. Yes?
You mentioned earlier that you thought that there were paraglacial deposits
in the Ediacaran, yes. It's a paraglacial involutions. So it's marginal, discontinuous permafrost structures. And it's only found in one horizon, which is pretty interesting because we have full glacial deposits in other parts of the Ediacaran. It's called the Hankelchu glaciation. It's found in China, and there's other deposits, actual tillites, in Siberia and a few other parts of the world at that particular time. But in South Australia, which was at a modest latitude, maybe 30 degrees north, not south, it's represented only by that convolute lamination, and also by frost boils. So where those convolutions reach the surface, that would be manifested as a frost boil, and these have been noticed for quite some time because the frost boils actually displace the fossils in rings. That has been argued to be a trace fossil of a mobile creature, but I think they're just frost boils.
So what implication would that have on current understanding of the Ediacaran climate?
It was cold. Surprisingly cold. The Ediacaran, of course, comes on the heels of the snowball Earth, which was really cold, in which just about the whole world froze over, but not the whole world. The paleosols, I've studied cryogenian paleosols in South Australia. We do have some non-glaciated periglacial paleosols with ice wedges and sand wedges, both, which are the sorts of things that you find now in the high Arctic, but they would have been at low latitude during the cryogenian. And then coming into the Ediacaran, it didn't really get all that warm. There are several glaciations through the Ediacaran. The Gasquias is one of the best known ones. There's another one recently discovered in Spain and Morocco, which is the same age as the sea level low stand that created the Newfoundland fossils. And then there's another one up, the Hankelchu, which is at the level of the 550 million year old one. So I think we can divide the Ediacaran by these three ice ages that go through it that are fairly distinct. And then going into the Cambrian, again, I'm not seeing tropical warmth. I'm not seeing a lot of tropical weathering. It all looks pretty temperate. The sun, of course, was a bit dimmer back then, quite a bit dimmer, maybe 10% dimmer, because the sun is on a trajectory of increasing solar brightness. Yeah.
Some of your early examples, you showed textures that looked like they had concretions in them, and some of the early on in the top.
Mm-hmm. Mm-hmm.
I'm not very familiar with soil development, but do you think that those textures that you were looking at are primary?
Yes.
I guess the reason I ask is because, in the western U.S., in like the Navajo sandstone,
Right.
we see.
Oh, the Moki marbles. Love those things. Yeah.
That's so cool.
Yeah.
They're not primary with respect to the Navajo itself. A lot of the hematite, uranium, thorium, helium dates that have been published for them are actually like 6 MA to 3 MA, possible biomediated mechanisms for their formation. So I guess the question is, you're dealing with porous, permeable rocks and basins, and some of the textures could reflect a fluid rock interaction event, the growth of autogenic phases and things like this that could be tens,
Right.
hundreds of millions of years after that happened. So does that complicate things?
Yeah, it does. It does. So the question is, could I just be looking at late diagenetic features and not early diagenetic features? So let's make a distinction here. Early diagenesis is after deposition and before burial, and late diagenesis is when you've buried it quite a way down, maybe 2-3 kilometers. And a lot of things happen in late diagenesis. We make coal out of peat, we make oil out of organic matter, and some people have thought maybe you can make nodules. I don't think you can make nodules that deep. And the reason is I think it's kind of a closed system. But let's say you can make nodules. The nodules would not look like the nodules we find. They would not be sand crystals that were leached out and then replaced by silica. The nodules would also not show the tight correlation between carbon and oxygen isotopes that we see, which has to be created by plants selecting for isotopologues of CO2. The nodules we find that are deep diagenetic, and there are a few around, and the crystals that we find, the crystals that you find in hydrofractured veins, they have a very different isotopic profile and a very different textural profile than the soil nodules that we get. Furthermore, diagenetic changes at depths of 2 kilometers have a gradient that reaches for half a kilometer or more, a kilometer, because you're dealing with a whole chemical and pressure field that is diffuse. We're talking here about differentiation of a soil profile that's only 30 centimeters thick over an entire basin. It doesn't seem likely to me that that's going to be a product of deep burial diagenesis, unless, of course, the nodules were altered by deep diagenesis, which is possible. So every paper I write, I have to get deeply into the weeds on illitization and on cementation and order of cements and cathodoluminescence and all that. We definitely, to get back to the early diagenesis, or what I prefer to call petagenesis, you have to take out the late diagenesis, or metamorphism in the case that I showed in one of those. Yeah.
Have you ever dated autogenic monazite with uranium-lead geochronology, or anything that you could texturally relate to an early part of that early history that might help back up?
The question is, have I ever dated monazite that could be related to the textures? And the answer is no. But I do have a field area in Western Australia where the monazite dating has been done, and it's actually been pretty helpful. But I have not gotten into where the monazite is in terms of the weathering rinds that I see yet. Yeah. There is dating, though, since you brought up dating, which is not my favorite topic, there is dating of calcareous nodules, for example, in Pennsylvanian age paleosols, and they're spot on. Uranium-lead dating of caliche nodules in Pennsylvanian age sediments, and they turn out to be very realistic according to the biostratigraphic information of the paleosols, the marine rocks that are above and below the paleosols. So that worked. And I think it would be possible to do that with some of these ediacaran carbonates as well. These are some of the things we want to do. I want to do magnesium isotopes. I'd like to do more dating. I've just sent some things off to date a particularly troublesome set of Archean paleosols in Western Australia by zircon uranium lead. All of this information is pretty useful. But why you need the paleosol vision is because we're focusing on 30 centimeter intervals. We're not taking a broad brush here. We've picked out something that we think looks like a paleosol on the field, and then we're tearing it apart. And that's not something that's been done before. And however it turns out, if it turns out not to be a paleosol, it's all good. What we're getting is detail. Yeah.
So, it seems like you're arguing that we're underestimating the paleosols from before plant invasion of terrestrial systems. So if you have a good estimate of terrestrial systems by the presence of root tracks, traces, after plant invasion, if you make the assumption that the proportion of Earth, this terrestrial Earth, was similar before and after plant invasion, you should say, well, if we have a good estimate that 30% of paleosols after surveys.
Oh, how does it look in the, what's the big picture this year? You want to know the big picture of what soils did?
Do people now argue before plant invasion there's 2% of Earth was paleosols?
No, they don't argue about, no, they know that there must have been some weathering going on out there because we have a world that is under control. You need weathering to keep the whole thing from flying off the rails. You need to sequester carbon by developing biomass on land and by weathering as well, by hydrolysis. I'm not quite the proportion of land that was paleosols, that's a silly way of looking. It's all soil of some sort. We would classify it as soil, and some of them are weakly developed and some of them are strongly developed. And it does look, as you go further back in time, that there were more weakly developed soils and then better developed soils that came along later. But what also happened in time is I've shown you some pretty major events, like the transformation of the world with the evolution of cyanobacteria and the great oxidation event in soils. Another really major event is when the land plants finally came on board. Not only did the cyanobacteria oxidize the world, they created a glaciation called the Macangeni glaciation. It's my supposition that when lichens evolved the first time, big lichens like Windermere, that created the cryogenian or snowball Earth. And the Ediacarans were just the sort of the tail end of that. When we had land plants on Earth, we have another glaciation, the Hernantian. And then when we had trees in the Pennsylvania, we have another glaciation. That's the Permocarboniferous glaciation. From the soil's perspective, it's very clear what's happening. The soils are getting deeper. They're getting more intensely weathered. In the Pennsylvanian example, for example, we had several soil orders invented for the first time ever. Ultrasols, alphasols, and histosols. Didn't exist before, but suddenly are everywhere. These are soils that are not just 30 centimeters thick, they're a meter thick. They're deeply weathered. They have massive communities of forests growing on them, and they pull down the atmospheric CO2 to create the ice age. It was undone not too long after because of the evolution of cockroaches and termites and dinosaurs until you went to the grasslands, which I'll talk about tomorrow, which I would argue create the ice age that we're currently in. So ecosystem evolution has paced the climate and the development of soils throughout Earth history. Is that sort of what you were after? That's probably too much, yeah. But the percentage, if you're asking about what the percentage of paleosol, what the percentage of land is, well, we have paleogeographic maps, that's all fine. And there was some degree of weathering on different parts of the landscape. But through each of these major evolutionary events in the biosphere, we see a stepping up of weathering.
Okay, let's hold it there. And let's give Greg another hand and thank him for